compare the lambda power 1 equation. So that we will be obtaining like this: h naught okay, psi n, it's a perturbed wave function now, psi n1, right, plus we'll be having lambda h prime psi n0. That psi n0 is nothing but our phi n. Okay, so yeah, this is equal to here you will be having en0 and what else, phi n, not phi n1, it's perturbed. So psi n1 plus en1 psi n0 or phi n, whatever, psi n0. Okay, this is nothing but phi n, and we have to substitute whatever we obtained for this particular thing in terms of degenerate states. So now I'm skipping one step here, just putting the value of phi n naught. Phi n naught is nothing but your phi n naught is nothing but your psi n naught is nothing but your phi n, right? Okay, so whatever you have taken here for phi n, this is something that you have to substitute over there. Okay, so you substitute and then you multiply it with one such we have taken. So what we are doing is we are substituting this entire term in terms of the degenerate subspace the eigenvectors or the basis of degenerate subspace, and we will multiply that equation with the another component on the same subspace. So when you are doing that, I just want to multiply the entire equation with phi n is a state and degeneracy I have taken here alpha, so there will be another component. So generally what we will do is multiply it with a beta, and whenever you have alpha value, that is going to be 1. That's it. Okay, you put that value, so this will give you phi n beta h naught psi n1 plus lambda h prime. Lambda h prime is nothing but hp, right? Sorry, the h lambda is not there. Okay, this is not there yet, comparing it. And what else? Phi n beta h prime phi n alpha will be there. Okay, this term we are not substituting here. We will be having a phi n alpha, and there will be a sigma running from alpha equal to 1 to f, and an alpha term also will be there on that term, which is equal to en0. Now change here en0 and phi n1. Here it's being multiplied with phi n beta and psi n1. Okay, plus now what we have to do is multiply the last term. So again, that's a number n1 sigma alpha 1 to f. Here what we have is phi and beta and phi and alpha, right? Okay. Did I skip anything? No. I skipped the constant A alpha. That will be there along with that on that term. Okay, now what will happen if this is exactly the same procedure? H naught acting on phi and beta, it will produce H naught is acting. It's not acting on phi n, it produces nothing but En. That is unperturbed Hamiltonian acting on this particular thing, and that is nothing but En. So En naught it will produce En naught into phi and beta and this coefficient quantity, and that is a quantity that you have on the RHS, and both of them will be cancelling, and what you will be having later is this term equal to this term. So both of them are having sigma alpha running from 1 to f. I'll write it commonly, sigma alpha running from 1 to f. Then what else is here? Okay, just pulling this En this side. Okay, this will be nothing but phi and beta h prime phi and alpha. Okay, and what else? Sigma A alpha is A alpha. So this is A alpha is common, you can take it together. So this quantity minus En1 sigma is common, and this quantity what is that? It's nothing but delta beta alpha. Whenever alpha and beta are same, that is the only time that is having any value, otherwise it's 0 into A alpha equal to 0. Well, this equation is really something very interesting, in the sense like, see, it's a homogeneous equation. It's not just a homogeneous equation, there are f number of equations, and on that f number of equations, if you see, whenever alpha is not equal to beta, whenever here alpha is changing, okay, alpha is not equal to beta, this En1 term is going to be 0. So alpha not equal to beta, that is not, it's going to be 0. Only they are having a value when alpha is equal to beta. So alpha equal to beta means yeah, it's a matrix. See, this is actually a metric component, right? An operator sandwiched between two things, so that is one element of a matrix, and you are varying here your alpha value from 1 to f, and this is actually you can write it in terms of a metric. It's yeah, you know how to do it. So if you want to write it in terms of an equation, so yeah, a matrix form we can write this entire quantity. You know, alpha is running from 1 to f, and beta is also actually running from on the same subspace, and the coefficient values can be from 1 to f. And okay, if you write that, one thing we have to notice is this is only going to have any En value, En1 value, or that first order correction in energy comes only associated with the terms where alpha and beta are same. In a metric, when alpha and beta are same, what sort of components are there? They are nothing but the diagonal components, right? The components of the matrix. So that is the only component where you will be having this En1 factor. Okay, write this entire thing in the form of a matrix. So yeah, this component we can write something like h prime h prime. It's nothing but we are living for the same state, so n is going need to be included. We'll write it as beta alpha kind of. So you can write this is h prime 1 1, the value you can take correspondingly. First value is beta, another value is alpha. So this will be having an en1 factor, en1, and this is going to be h12, h22, sorry, h13, 13, etc. to h1 alpha, and h21, h22 minus en1, etc. h2 alpha, and finally you will be having h f, right, the last component, and somewhere you will be having other terms. Okay, so you'll be having a matrix like this when you're doing the problem, and what we have to do is see phi and alpha. We know that this will can do in different ways. So this is equal to 0 means what we have to do is you take the determinant of that quantity, and that will be equal to 0. If it has to have any so if it has to have any non-zero solutions, non-vanishing solutions, then we must have this determinant going to be equal to 0. So once you take the determinant of this entire matrix equal to 0, you'll be having an equation which involve en1 on f order, right? It's a matrix of f order, the degeneracy whatever is there, that is order of this polynomial in en. So if you solve that entire equation, you will be having f number of solutions for your en1, and that is going to be the different values of your energy correction. So that is a way of doing, or the easier way to do this problem is to diagonalize the entire matrix, and you can find out the value of en1. Yeah, so you diagonalize it and find out the value of en1, and once you have en1, you know the first order energy correction. So this is actually in this case we'll be having how many roots? En1 will be having f roots. In this f roots, all the f roots are different. If you are getting different value for all the roots are different, then what will happen for the energy value? Energy En is going to be En0 plus lambda into that quantity, and all the energy levels will be different, and the degeneracy is completely lifted. Degeneracy is completely lifted. If all the roots are same, all the roots are having same value, en1 all are having same value, then there is no degeneracy is not lifted. It's there as such, not lifted. If the value is lying between something less than f, then it is just partially, or some of the en1 values are same and others are different. So in that case, so we'll be having fruits, some roots different. In that case, you have a partial lift on your degeneracy. Okay, so that is a interpretation of this part. And if we find out this en1 after doing this whole process, how do you find out your a alpha? You can find out a alpha from this equation, right? This is involving a alpha. Once you know the en1, you can find out the quantity a alpha corresponding to each ion value. So a alpha corresponds to each ion value, you can find out. So that is the moment once you know a alpha, you will be able to calculate, or you will be able to get your zero order wave function, this quantity phi n. So see, to calculate the degenerate state, how the degenerate state, yeah, if you want to find out the coefficients of this degenerate state, you need to have your first order energy correction. Without that, you cannot calculate this a alpha. And that makes sense because, you know, if there is no perturbation, if there is no energy change at all, right? So that energy change is coming because of the perturbation. And once you have that particular quantity, then only yeah, this will be able to calculate. So the idea here is that what is different compared to the non-perturbation, non-degenerate perturbation is this thing, where in the non-degenerate perturbation theory we have to find out first order energy correction. Now with first order energy correction, you will be able to calculate the state correction in first order, and second order with using second order you can calculate the state correction in second order, and so on. But in this case, to find out the zero order correction in the wave function, you need first order correction in the energy, and that is same as you go higher and higher order. If you want to find out the first order correction in the wave function, you need to go to second order correction, or the third equation in our lambda square equation you have to utilize. So we will not be doing that part. So this is something that we have to find out, and you know how to find out a alpha. And yeah, this quantity phi n, or this is nothing but psi n. Okay, if you are not going for higher order, this is nothing but psi n, right? Psi n is the perturbed Hamiltonian, but see, we are taking it only up to the zeroth order, so this is nothing but psi n, or psi n is nothing but this quantity